All right, welcome back to more hydraulics. Let's just jump right into it. So first question we got, a rectangular concrete channel is 4 meters deep and 8 meters wide with a downward slope that decreases 1 meter every 1 kilometer. Calculate the flow in the channel. So immediately this is going to be a case of open channel flow. Now, when you think of open channel flow, think of Manning's equation immediately. This is going to be the go-to equation for open channel flow. So I'm going to take that from page 185 of the FE handbook and I'm going to write that down. All right, so here's our Manning's equation. And first thing I want to point out is you can have two different numbers that can go here. This is going to be 1 because we're using SI units. If we were using American units, it would be 1.49. So the other terms in this equation, we got area of the channel, should say cross-sectional area, R, the hydraulic radius, and S is the slope. So let's go quickly through what we have for this equation. So first is N, which is the roughness coefficient, and we were told that the channel is concrete. So for concrete channels, N is going to be equal to 0.013. So in the FE handbook, there is no table for these roughness coefficients for Manning's equation, so they'll likely just give you that. It's also just good to know, again, if you go into water resources, knowing that Manning's roughness coefficient for concrete is 0.013, you'll probably use that a lot as well. So going through this equation still, we have the dimensions of the channel, so we'll be able to find A. We don't have the hydraulic radius, and we were given the slope as well. So let's go ahead and find the hydraulic radius. So I wrote out here the equation for hydraulic radius, and it's going to be the cross-sectional area, A, over the wetted perimeter. So the wetted perimeter is just the parts of the channel that are actually in contact with the water. So we can first easily find the cross-sectional area with just doing this, 4 meters times 8 meters. That's going to be equal to 32 meters squared. And then for the wetted perimeter, we got two sides with that are 4 meters. So we'll do 2 times 4 meters plus 8 meters will give us 16 meters. So then our hydraulic radius is just going to be equal to 32 meters squared over 16 meters, which will be 2 meters. So I said earlier we had our slope, which was technically not true. I meant we had everything we need to find the slope. So that'll just be rise over run. So slope's going to be equal to Z1 minus Z2 over L. So we were told the slope decreases 1 meter every 1 kilometer. So Z1 minus Z2 is just going to be 1 meter. Then 1 kilometer is 1,000 meters. So our slope's going to be 0.001 meter per meter. So now we have everything to solve for the flow. So here's our Manning's equation again. So let's just go ahead and plug and chug with everything we got. It'll be 1 over 0.013 times our cross-sectional area, 32 meters squared, times our hydraulic radius. That'll be 2 meters, 2/3 power. Finally, multiply by the square root of our slope, which will get us 123.5 cubic meters per second. And there we go, first question done. Okay, so on to the second question. So we got a 36-inch circular concrete pipe flows at a depth of half full. The slope of the pipe is 0.025 foot per foot. Calculate the velocity and flow rate in the pipe. So first of all, don't get thrown off that the flow is within a pipe. Just because it's in a pipe doesn't mean it's closed conduit flow. So it's flowing at half depth, which still means it's open channel flow. So again, we're going to be using the Manning's equation. So here's our Manning's equation, and this time we're going to be using 1.49 instead of 1 because in this problem we're using American units. So first step here is to find the cross-sectional area. So we know the pipe is flowing at half full. So what we can do is we got pi r squared for area of circle and just divide that by 2. So we can find that. So our pipe in our problem is 36 inches. That's diameter. So our radius is 18 inches. And we'll divide that by 12 to convert that into feet. Square that, divide it by 2. And then we'll get 3.53 square feet. So now we got A And just a reminder that N roughness factor is going to be still 0.013 because it's a concrete pipe. We got those two terms. Now let's find the hydraulic radius. So hydraulic radius, cross-sectional area over wetted perimeter. We have the cross-sectional area, so let's find the wetted perimeter. So pipe is flowing at half full, so it's a half circle. That'll just be pi times radius. That'll be pi times 18 inches divided by 12 for feet, and that'll be 4.71 feet. So there's our wetted perimeter. So now we can find the hydraulic radius. That'll be our cross-sectional area, 3.53 feet squared over 4.71 feet will give us about 0.75 feet. So now we have what we need to calculate the velocity and flow rate. So for velocity, I'm just going to quickly show this. They give you this equation in the FE book anyway, but I'm just going to show you where that comes from again. So you can write Q here on the left side as equal to VA, continuity equation, and then just cross off the A's on both sides. So there's our velocity equation. So let's plug and chug. So 1.49 over 0.13 times the hydraulic radius, 0.75 feet, 2/3 times 0.025 feet per foot. And that'll give us 14.96 feet per second. So there's our velocity, and instead of going through the big equation here again for the flow rate, we can just use the continuity equation, Q equals VA, to find our flow rate. So we got Q times our velocity we just found, and our cross-sectional area of 3.53 feet squared get us 52.8 cubic feet per second. And there you go, second question done. So I hope those questions helped, and I'll see you in the next one. Thanks.